In this short video, I am going to discuss paired comparisons. After you've done an analysis of variance, you want to see if there are differences between means, if there are more than two means in your groups. And so I'd like to talk about the difference in doing paired comparisons with the general linear model repeated measures, the GLM repeated measures in SPSS, and the mixed model in SPSS. And let's just take a quick look to kind of see what the problem or the issue is. Here is a general linear model. We're using the Chow data. For the general linear model, the data is run horizontally. So each subject has a year, we have 6 years, has a year represented by a column of data. So let's take a quick look. So we have the data in this direction. Now we get our estimates, and then we look at our paired comparisons. And this is year 1 versus year 2. In terms of our column headings, it's AL0 through AL5. AL0 is given a 1, AL5 is given a 6. So when we compare 1 to 2, here's the mean difference between these two. This is the standard error. You divide the difference by the standard error, you get a t-test, and you can compute the significance. Now, if we look down here, we see all these standard errors are different. And one of the questions we have is, where do these standard errors come from? Now, let's look at the same thing for a mixed model. In the mixed model, the data are organized a little differently. Here, we have axial length, and we have year. In this case, all the year zeros are together, years 1s, 2s, 3s, 4s, and so forth. So we have a slightly different way of organizing, but paired comparisons still come out the same. 0 to 1 is the difference, and this is the standard error. You get the degrees of freedom and the significance. And one thing you should point out is all the standard errors are the same. Where do these come from? So there are actually many ways of doing multiple comparison studies, many ways of calculating standard errors, and we're just going to take a look at what is a reasonable kind of way. It seems to me that if we're doing repeated measures, those are like doing a whole bunch of t-tests. So let's say we had a whole bunch of t-tests in which we look at AL0 versus 1, AL0 versus 2, 3, 4, 5, AL1 versus 2. These are all the possible combinations of t-tests. And they're paired t-tests. And while there are issues of multiple comparisons, in general, the standard error and the means should be relatively close in the ANOVA as in the paired t-test. I mean, the paired t-test is something we can get a handle over, and we would expect that the analysis of variance to be similar. So in the case of SPSS, let's look at our standard error, which is for AL1, AL0 versus 1, AL0 versus AL2. It's 0.02, 0.03. Let's see what it is in our paired comparisons in the one-way general linear model. 0218, 0334. 022, 022, that's 0228, 033. You can see basically, with a little bit of a rounding error here and there, the post hoc comparisons when we do a post hoc comparison, it is the same standard error as the t-test. Now, that seems to make some sense. These are differences I think we can trust in a way because they're t-tests. Now, it's somewhat well, let's go to the mixed model. Now, as a reminder, the mixed model does not have all these different standard errors. It just has, oh, actually, no, where is it? Okay, right here. It just has one standard error of 0.038. Now, the mixed model kind of goes along the philosophy that there's homogeneity of variance. You're kind of assuming all the variances are equal. And when you have all of these combinations, you're basically sampling, and you're just, and then if you put them all together, you get a good sample of what the standard error really is, the overall population standard error, as we go out and sample these various things. Now, I will say this changes somewhat. We're using compound symmetry, so we assume that all these errors are equal. We'll find a little bit of a difference when we choose different covariance structures. But as far as the paired t-test, this is, given that definition, these are all the same. Now, where does this 038 come from? Well, if we look at our if we look at our paired t-test, these are our paired t-tests, these are the standard errors. Suppose we take the average, 0.036. That's the average of these standard errors. Now, actually, a little bit better average is to sum these guys. Oh, sum the square of these guys. This value right here is this value squared. And then if we sum those squares, divide by the number of values that there are, which is 15 pairs, and we squared them, so let's take the square root of that, we get maybe a little bit better estimate of the average, 0.038. Now let's go back. Oops. 0.038. So that's where that comes from. Instead of using individual standard errors for everybody, it takes the average standard error and divides it into everybody. So that's the basic difference between that GLM and the mixed model. As a reminder, go into our syntax. When you go in and you hit compare, you don't get, or when you ask for, well, let me show you here. Let's go to general linear model, repeated measures. Oh, I don't know which one it is. Let's go to this. Analyze, general linear models, repeated, factor, define, options. Compare main effects. It does not automatically compare interactions. which is somewhat troubling because you wonder, is it not doing it because it doesn't believe it's a good idea what you're doing? And that's kind of what we're testing here. Is this a good idea or not? So we paste it into syntax and we force it to compare by typing in this command. Oh, that's when we get to the interaction. We're not there yet. We're still at a main effect in a one-way, so it automatically does this. So we'll address that other issue later. So that's where this comes from. We get the simple effects and we check it out, and we see that basically the GLM repeated measures is doing individual paired t-tests, and the mixed model is doing individual paired t-tests with a pooled standard error term, average standard error term, also called pooled. All right, now we have another situation when we did the chow data. We had axial length over years, but we also had a lens type. They were either spherical or aspherical, and this was between subjects. Subject either had spherical contact lenses or aspherical ones, and so we wanted to see how much growth we got under each one. And that's a mixed model, and it's kind of confusing because this is a mixed model because it mixes between and within subjects, as opposed to the maximum likelihood mixed analysis of variance, where mixed refers to random and fixed factors. So it's sort of the same thing but different. Okay, let's look and see what we have here. And I'm going to be focusing on the interaction term. And again, as I mentioned a minute ago, when we look at lens type by year, we can force the lens type comparison. So we're basically looking at, is there a difference between lens type at each year of growth? We can do that by adding this phrase, which doesn't automatically get printed out. Compare lens type adjusting, or well, this is a post hoc adjustment, which is least significant difference, which is no adjustment. So we're not really adjusting for any for p-value. You can adjust for Bonferroni, something like that, if you are so inclined. All right, but let's just see what we get with this. And so we have our mixed model in the GLM. We get our within subjects, and it has the error term of 0.119 down here and all these f-tests. And it has between sub-tests. We've covered this before. And then you get your estimates again. The estimates are exactly the same. Standard errors are a little bit different because now we have accounted for some of the variability in terms of lens types. So they're not going to be the same as the estimates up here. 0.080, 7675. They're really close, 7.4 and so forth. So anyway, well, that's a general linear model. Where's next? 0.07, oh yeah, they're different. Well, and again, we get this constant value. So the question is, well, we already talked about that one. Whoops, we want to come down here to the estimates. 0.077, all the same. 0.036. Now, 0.036 is the standard error there for the general linear model. When we're comparing the lens type, it's 0.161. So we have 0.154s all the way down, and the general linear model different ones. Now, this is spherical versus aspherical at baseline, at year 2, 3, 4, and so forth. And these are the differences. These are the standard errors. We see significance at 0.805, 0.805. Now let's look and see this is the general linear model. They're different. And again, in this case, we're looking, our equivalent t-test is an independent t-test that is at each year. So we would be pretty happy if our significance was similar to the independent t-test, because again, we feel comfortable knowing when we do a t-test between two things that those should be somewhat similar in terms of the differences between means. So let's see, let's look at significance. 0.805, 0.321, 0.004. So t-tests, p-value 0.805, 0.321, 0.004. So we see once again that the general linear model, on the mixed model, the pairwise comparisons are equivalent to a t-test, an independent t-test. Now, what about the mixed model? When we look at its pairwise comparisons, it has same sort of thing, but now a single 0.154. Now, where does that come from? Now, this gets a little bit more complicated. Well, not in the first sense of talking about stuff. Let's go back to our Excel file. And we have independent t-tests right here. Oh, here they are. And we see the standard errors. But here we see this again is that average. So we're squaring the standard error, then we're summing it, dividing it by 6 for the number of tests we're doing. And we come up with around 0.15, 3 or 4. And in our output here, 1.154. So again, we see the mixed model uses the pooled error that is very similar to the independent, pooling the standard errors across the 6 separate independent t-tests. And again, this is not a bad strategy if the variances are pretty close, because you're making the assumption that you're gathering a sample, and now you're taking the average of 6 sample denominators, and you can get a better estimate of the denominator and get a more accurate estimate of the p-value. Okay. Now, if we were doing this, is there a way to do it without calculating independent or paired t-tests. Actually, yes there are, or yes there is, but that's not a bad way to do it. Once you have established that you have a significant interaction effect and it's legitimate for you to go and compare things across years. If you don't have a significant interaction, then you would go to main effects. If those aren't significant, then there's no difference, and finding differences doing this would be spurious and not a good idea. So the significant interaction is protecting you somewhat against spurious findings. But again, where do we find these differences? So let's come to our Excel sheet. And here's our one-way repeated measures. And what is our target? Our target is looking for, well, actually, if you're doing the general linear model, you basically have, there's no problem. It gives you the right thing. The question is, if you're doing a mixed model, what is the strategy for finding the error term? So in mixed models, this is the one way by year. We recall that this estimate, this value right here, is the variance. If we take the square root of that, we get the standard deviation. And then if you think about a paired t-test, what is a paired t-test? It's taking each individual difference. An independent t-test is taking all the differences and summing and like. In this case, or in an independent t-test, you take the mean of one group minus the mean of the other group divided by the standard error of the difference. In a paired t-test, you calculate separate differences for each pair, and then you divide it by the standard error of those differences. So this standard error that we get, which is taking the standard deviation, remember the standard deviation is the square root of the estimate, and then we divide the standard deviation by the square root of n, which in this case is 94. And we get 0.038, which is the comparison down here. So this is a little bit different than the independent t-test, which takes the difference between means to get at it. So let's look at that one. If we come down here, we see our covariance term. Now this one is a little more complicated. Instead of it being this value, which is the CS, the compound symmetry diagonal estimate, or the CS covariate instrument, we actually have to add these two together, because it's both between and within when we're looking at the difference between means. And then we calculate the square root of that total to get the standard deviation. We have the n of 94. We get the standard error by taking the standard deviation, dividing by the square root of 94. That gives us the standard error. But then the standard error of the difference for between subjects, it's the sum of the variance. Now we assume they're the same. So the two groups, we assume the variances are the same. And we've estimated this pooled variance that's everybody. And you're going to sum the two. or you take 2 times this pooled value right here. And so the estimate is 0.154. We come down here, we see that for all the paired comparisons, the standard error now of the difference is 0.154. So the interaction term for the mixed model design is a little bit more complicated, but what it still does is come out and gives us that. But again, that 0.154 is equivalent to the average of the standard errors for the independent t-test. And that's basically where those values come from. And we can be reasonably comfortable that it's equivalent to t-tests. It's definitely equivalent. It's exactly the same in the general linear model. And it's the same in the between subjects model with a pooled term. One other thing that I should point out is when you pool the values, that actually, because you're adding some power and sensitivity when you pool things. And in the case of SPSS, what they do when they're pooling this is well, they're giving you a few more degrees of freedom somewhere along the line. Okay, 930. Oh, what was that? Let's type by year. Well, when you're looking at the individual years, they add up they give you a lot more degrees of freedom to give you a sensitivity, but the one-way year analysis is less important than this one. But for this one, you can compute your confidence intervals just like you've done in the two-way analysis. You just have to use this new standard error. This one that uses the total. So that's the difference when we had a two-way design with no repeated measures. We used the square root of the covariance term, but here, there it is. Rather than the square root of this term like we would do if there were no repeated measures, we use this term when we're comparing between group the simple effects of is there a lens effect for each year. So difference between the groups on a single within factor, you take into account both these types of variance and you go through your little procedure and you find that. But this would be the standard error you would use in the 84% confidence interval to give you the same answer as this t-test, standard error of the difference. So this is your confidence interval standard of error. This is the standard error of the difference used in calculating the t-test between two groups. This standard error goes plus or minus the t times this value on each individual mean. So non-overlapping confidence intervals based on this value are significant. It's not this value, and it's not this value. It's this value, which is the sum of these two values. A little bit different. Other than that, everything is pretty much the same as we've done before, with the exception that the standard error in the repeated is the standard error of the differences, not exactly the same as for each mean. Okay, that's it.